Hello everyone, welcome to Module 6, Lesson 2 of Mastering Ethereum. Imagine constructing a secure vault to protect valuable treasures. Similarly, building secure smart contracts on the blockchain is essential to safeguard assets and data. Today we will delve into critical security principles necessary for robust and trustworthy smart contracts. We will explore best practices such as input validation, error handling, and proper use of cryptography. By mastering these principles, you can significantly enhance the security posture of your smart contracts and protect them from malicious attacks. The principle of least privilege dictates that a program or user should only have the minimum permissions necessary to perform its intended task. Consider a high security laboratory where only authorized personnel can access specific areas. The principle of least privilege ensures minimal access to reduce risk. Let's look into this through an example. The least privilege contract in this Solidity aims to adhere to principle of least privilege. It has state variable owner of type address, which stores address of the owner of the contract, editor, which is the mapping from addresses to booleans, where each address represents an editor, and the boolean value indicates whether the address has editing privileges. The constructor function is executed only once when the contract is deployed. It initializes the owner variable with the address of the account that deploys the contract. The addEditor function allows the owner to grant editing privileges to other addresses. It takes an address editor as input and adds it to the editor's mapping with the value set to true. However, it includes a require statement to ensure that only the owner can add editors, preventing unauthorized changes to the list of editors. The edit function represents the logic of editing operations. It verifies if the address calling this function is registered as an editor by checking the editor's mapping. If the caller is not an editor, the function will revert with an error message, not an editor, preventing unauthorized editing. In summary, the least privileged contract implements the principle of least privilege by designating the owner as the entity with the authority to grant editing privileges to other addresses. This helps minimize potential damage caused by unauthorized actors or errors and enhances security by restricting editing privileges to specific accounts. The next security practice is the use of well-audited libraries. Imagine having a library of pre-tested, reliable tools at your disposal when constructing a building. Using well-audited libraries in smart contract development provides similar benefits. Leveraging popular libraries such as OpenZeppelin can reduce development time, minimize vulnerabilities, and enhance code quality. These libraries have been extensively tested, offering secure functionalities ready to be integrated into your smart contracts. This snippet includes an OpenZeppelin library ownable contract providing a convenient way to control ownership and access control in Solidity smart contract. By using well-audited libraries, you build on solid foundation of proven secure code, much like using trusted tools for construction. Magic numbers are literals used in code without clear context. They make code harder to understand, modify, and maintain. Think of magic numbers as coded messages on the treasure map that are hard to decipher. In smart contracts, magic numbers can obscure the code's functionality and increase the risk of error. Let's look into this through this example code snippet. The avoid magic number contract in Solidity exemplifies the use of constants to enhance code clarity and reduce vulnerabilities. The min balance is a state variable. By utilizing a constant variable, the code ensures that the value of minimum balance is clearly defined and can be easily referenced throughout the contract. The check balance function compares the provided balance with the defined min balance using the greater than or equal to operator. It then returns a Boolean value indicating whether the provided balance meets or exceeds the minimum balance requirement. In summary, the avoid magic numbers contract serves as an excellent example of encapsulating significant values as constants rather than using hard-coded, unexplained literal numbers directly in the code. This approach improves code readability and maintainability and reduces the risk of errors caused by unclear or hard to modify values. Avoiding magic numbers ensures clear and maintainable code, just as using legible instruction makes finding the treasure easier. Securely handling Ether transfers is crucial for preventing vulnerabilities and ensuring smooth contract operations. Proper Ether transfer handling involves using call function for greater control and error handling. Imagine transferring delicate antiques requiring careful handling. Ether transfers in smart contracts must be managed with similar precision to avoid disruptions and ensure security. Let's look into this through an example. The Ether handling contract in Solidity is designed to handle Ether in a secure manner. The send Ether function is public and payable function, meaning it can receive and handle Ethers. It takes an address payable recipient as parameter, representing the address of the recipient to whom Ether will be sent. Inside the send Ether function, it uses the low-level function recipient.call to transfer the received Ether to the specified recipient address. The .call function allows for more control and flexibility in Ether transfers, giving the ability to check the return values of the transfer. After the Ether transfer, the function employs the usage of bool success equal to recipient.call line to capture the success status of the transfer. The unused variable is denoted by empty assignment to comply with the syntax of the low-level call. Following this, a require statement is used to ensure that the ether transfer was successful. If the transfer fails, the string transfer failed is provided as the error message. The send ether function within the ether handling contract effectively manages the transfer of ethers to the specified recipient address while carefully handling potential success or failure outcomes of the transfer in a secure manner. This approach aligns with the best practice for handling ether transfers to prevent potential vulnerabilities and ensure smooth contract operations. Securely managing ether transfers, like carefully handling of delicate items, ensures smooth and safe operations of your smart contract. SafeMath is a library in Solidity that helps prevent arithmetic errors such as overflow and underflow when performing mathematical operations on integers. It was widely used in the older versions of Solidity prior to 0.8.0. Picture arithmetic in smart contracts as solving intricate puzzles needing precise calculations. SafeMath acts as a reliable solver, preventing errors and vulnerabilities. In the provided SafeMath example contract demonstrates how to use SafeMath library for safe arithmetic operations in Solidity. It imports SafeMath from OpenZeppelin and uses it to provide a safe add function which adds two UN256 numbers while preventing overflow. This contract showcases safe addition. Using SafeMath ensures precision and reliability in your contract's arithmetic operations, much like solving puzzles with a fail-safe method. Event logging captures user interaction, state changes, and transaction details, aiding in auditing and debugging. Think of event logging as maintaining a detailed journal that records significant events. In smart contract, event logging provides transparency and traceability. Let's look into this through this example snippet. The event logging contract defines an event called transfer, which logs the sender's address from the recipient's address to and the transfer amount value. When the transfer function is called, it emits the transfer event, allowing external listeners to track transfers on the blockchain. This provides a transparent way to log activity in the contract. By logging critical actions, you maintain transparency and accountability, much like keeping a well documented journal. Circuit breakers enable pausing smart contracts during emergencies, allowing for analysis, mitigation, or issue resolution. Imagine a circuit breaker in an electrical system that prevents overloads. In smart contracts, circuit breakers halt operations during emergencies to prevent catastrophic failures. Let's understand it through this example. The circuit breakers contract is a security pattern that provides a mechanism for pausing certain contract operations in case of emergencies. Stopped is a Boolean state variable and is used to indicate whether the circuit is currently open, that is, it is in emergency situation, or closed, that is, it is in normal operation. Owner is a variable of type address that represents the owner of the contract. Stop in emergency is modifier is designed to restrict certain functions from executing when the circuit is in an emergency state. Only owner is modifier that restricts access to specific functions, allowing only the owner of the contract to execute them. The constructor function initializes the owner variable with the address of the owner that deploys the contract. The toggle contract active function is marked as public and can be executed by the contract owner. It toggles the state of the stopped variable, effectively opening or closing the circuit. The withdraw function is marked to be callable only when the circuit is not in emergency state. It likely contains the logic for the withdrawal of funds or other critical operations. The circuit breaker contract exemplifies a crucial security measure by providing a structural approach to managing potential emergencies or crises within a smart contract. By controlling the contract's operation based on the state of the stopped variable, it seeks to enhance the resilience and overall security of the contract system. External contract calls can introduce vulnerabilities and increase the attack surface of your smart contract. Limiting these calls help to minimize the potential for exploits and improve the overall security of your code. Restricting external call involves carefully assessing the necessity of each call and exploring alternative approaches to achieve the same functionality without relying on external contracts. Strategies include using internal functions, pre-computed values, or minimizing data dependencies on the external contracts. Modifiers in Solidity offer a powerful way to enhance code reusability and enforce consistent checks across your smart contract. They essentially act as functions that can be applied to other functions executing their code before or after the main function's execution. Error handling and assertions are crucial for ensuring the reliability and robustness of smart contracts. They help prevent unexpected errors and safeguard against malicious attacks. In Solidity, you can use require, assert, and revert to handle different types of errors and enforce invariants. While require and revert are typically used for handling external conditions, assert is designed for internal checks and should only be used to catch errors that are unlikely to occur in normal operation. Each of these functions throws an exception if the condition is not met, halting contract execution and returning any funds. The Solidity code defines a smart contract error handling with a function divide that safely performs division of two unsigned integers. The key aspects are before performing the division, the function checks that the divisor b is not 0 using require. This prevents division by 0 which would cause a runtime error. The division a by b is performed and stored in the value result. The function uses assert to ensure that the division was performed correctly. This is an internal consistency check to catch any unexpected behavior or bug. Finally, the function returns the result of the division. The require and assert statements provide robust error handling, ensuring that inputs are valid and internal logic is consistent. Designing contracts with upgradability in mind allows for seamless modifications and enhancements. Using constants and best practices ensures smooth transitions. Consider software updates that improve a device's performance over time. Similarly, smart contracts may need updates without disrupting their core functions. The upgradable contract exemplifies the concept of upgradability in smart contracts. Implementation is a public state variable of type address that holds the address of current implementation of the contract's logic. The upgrade function is marked as public and allows for update of contract logic. It takes an address new implementation as parameter representing the address of new implementation contract. Upon calling this function, it updates the implementation state variable with the provided new implementation address. This enables the storage of new logic's address, effectively upgrading the contract's functionality. The fallback function is designed as external and is invoked when a call is made to the contract without matching any of its function signatures. Without the fallback function, it delegates the call to the implementation contract using low-level delegate call assembly code. This enables the contract to redirect function calls to a new implementation, preserving the state and data of the original contract. The use of delegate call along with assembly code allows the contract to execute the logic of new implementation without modifying the contract storage or state variables directly. It also handles the return values and exceptions, reverting the call if it fails and returning the result if successful. In summary, the upgradable contract represents a powerful mechanism for maintaining and updating smart contract logic without disrupting the state and data stored in the contract. This approach provides flexibility for patching vulnerabilities, implementing new features, or fixing bugs without requiring a complete contract redeployment, enhancing the long-term functionality and security of the smart contract system. Embracing upgradability in your contract ensures they remain adaptable and relevant, much like keeping software up to date. Access control is fundamental security principle in smart contract development. It ensures that only authorized entities can interact with specific functions or parts of the contract. By implementing robust access control mechanisms, you can prevent unauthorized access, manipulation, or exploitation of your contracts. OpenZeppelin provides a suite of tools for implementing access control. One of the most widely used is Ownable Contract, which grants the contract deployer ownership and exclusive control over the specific functions. Its implementation can be seen in the code snippet provided below. Thorough testing is essential for ensuring the robustness and reliability of smart contracts. This involves a comprehensive approach that covers various aspects of the contract's functionality, from unit testing individual components to integration testing interactions between different parts. Each step contributes to a secure and dependable system. In the following snippet, the code testing is done in JavaScript using Truffle. The given Solidity smart contract, my contract, contains a single function called my function that takes a uint256 value as input and returns value plus 10. This function is marked as pure, indicating that it doesn't modify the contract state. In the provided JavaScript test script using Truffle, the contract my contract is imported through artifacts.require to interact with the deployed contract instance. The test is written using Truffle's testing framework, where test is defined with it should perform the expected behavior async, describing the expected behavior. Within the text function, the contract instance is obtained by calling await myContract.deployed to interact with the deployed contract. The my function is called using instance.myfunction.call to retrieve the return values without modifying the contract state. The test asserts that the result obtained matches an expected value using assert.equal result expected value. The value should match. This test script aims to verify that my function within the my contract behaves as expected by comparing the returned result with the expected value. Tests like these are crucial for ensuring the functionality and correctness of smart contracts, especially when deploying updates or changes to the contract logic. Multi-signature wallets enhance the security of critical operations by requiring multiple parties to authorize transactions. Instead of a single private key controlling fund, a multi-signature wallet utilizes a threshold scheme where a predetermined number of signatures are needed to execute a transaction. Consider a scenario where a decentralized organization manages funds. A multi-signature wallet could be configured to require 3 out of 5 authorized individuals to approve any withdrawal. This ensures that no single entity can unilaterally control the fund, mitigating the risk of unauthorized access or malicious activity. Let's look into this through the multisig wallet contract. Min signatures is a constant event variable with a value of 2 representing minimum number of signatures required for transaction execution. Owners, an array of address representing the owners of authorized parties of the multi-signature wallet. Transaction count, a public event variable tracking the total number of transactions submitted. Transaction is a struct type that captures the details of transaction including the destination address, value to be sent, execution status, and the count of collected signatures. Transactions is a public mapping that stores transactions with their respective IDs as keys and transaction details as values. Signatures is a mapping that keeps track of the signatures collected for each transaction, associating the transaction ID with the signer's addresses. Only owner is modifier that checks whether the function caller is one of the designated owners of the multi-signature wallet, ensuring that only authorized parties can execute specific functions. The constructor function initializes the owner array with the addresses passed as argument. The submit transaction function allows an owner to submit a new transaction by providing the destination address and the value to be sent. It increments the transaction count and records the transaction details. Owners can use the signed transaction function to add their signature to the transaction. If the required number of signatures defined by min signatures is reached, the transaction is then executed. The execute transaction function is an internal method responsible for executing a transaction. It checks if the required number of signatures is present, then proceeds to execute the transaction, sending the specified value to the destination address. In summary, the multisig wallet contract showcases a secure and robust approach to handling transactions by leveraging multi-party authorizations. This pattern is especially valuable in scenarios where high security standards and safeguards against unauthorized actions are essential, such as managing funds in decentralized organizations or executing critical operations in trustless environment. Time locks are valuable security measures in smart contracts. They introduce a delay before sensitive operations can be executed. This delay gives time for stakeholders to monitor the situation, detect potential malicious activity, and take necessary action to prevent unauthorized transactions. Implementing a time lock involves setting a future timestamp as the release time. Only after the release time has passed can the desired action be executed. This mechanism prevents immediate execution, giving time to verify the authenticity of the request and ensure it aligns with the intended purpose. The Solidity Code defines a smart contract time lock that allows an owner to withdraw funds only after a specified release time. Here are the key points. The state variables include release time, which stores the time after which withdrawal is allowed, owner, which stores the address of the contract owner, constructor takes a U1256 parameter release time and sets the release time to this value, checks that the release time is in future using release time greater than block.timestamp, sets the owner to the address that has deployed the contract. Message.sender. Withdrawal function can be called by the owner to withdraw funds. It also checks that the current time is at or after the release time using require. It then checks that the caller is the owner using require message.sender equals to owner. This contract ensures that funds can only be withdrawn by the owner after the specified release time. Regular code reviews and security audits involve meticulous examination by peer developers and security experts. They identify potential bugs, security flaws, and design issues promoting best practices. Think of code reviews and audits as regular health checkups for your body. Just as doctors identify and prevent health issues, code reviews and audits help uncover vulnerabilities in your smart contracts. Conducting regular code checkups ensures your contracts are healthy and secure, much like regular medical checkups maintain your health. Clear and thorough documentation explains the purpose, inputs, outputs, and side effects of each function. It reduces errors, enhances collaboration, and ensures long term code sustainability. Imagine documentation as a detailed guidebook for an expedition. Just like a guidebook helps travelers navigate through terrain, comprehensive documentation helps developers understand and maintain the code. Clear and thorough documentation explains the purpose, inputs, outputs, and side effects of each function. It reduces errors, enhances collaboration, and ensures long term code sustainability. Proper documentation helps developers navigate complex code, similar to how a guidebook aids travelers in unfamiliar territories. Smart contract developers must stay informed about the latest security updates in Ethereum community. This involves following the security forums, participating in discussions, and updating dependencies regularly to incorporate new security patches and mitigate known vulnerabilities. Picture staying updated on security vulnerabilities and best practices as equipping yourself with the latest maps and tools for safe travel. Staying up to date with security updates ensures your smart contracts are protected from evolving threats, much like how updated travel gear ensures safe and smooth journeys. This brings us to the end of our lecture. We have now scaled the mountain of the security practices for smart contracts, well equipped with knowledge and tools. In summary, it's crucial to implement secure coding practices, prioritize contract upgradability, handle ether transfers properly, conduct regular code reviews, and stay updated on security development. These best practices collectively enhance the robustness and reliability of smart contracts. By integrating robust security measures and fostering a culture of continuous improvement, you can bolster the integrity, reliability, and trustworthiness of your blockchain based application. Remember, smart contracts are as secure as the effort and diligence put into their development and maintenance. Thank you for spending your valuable time.